a few weeks ago at one of the weekly Rust lunches that Ben has been hosting, I gave kind of an informal, just showing some of the stuff that I was working on. And he thought it was really interesting and asked me to give a talk. So here we are. So I don't know, does everybody know what a turbofish is in terms of Rust context? Yes, I see some big hands. I bet there's some people that helped invent the turbofish here. Turbofish is actually one of these fun things I loved about the language, and it goes pretty far back. And so I don't know all of the history of when it was invented or how it got popularized, but it seems to be enough of a thing now. So, you have a small community of people that understand what it is. So anyway, so turbofish also is the name of my boat. So this is an offshore sailing boat. It's meant to go fast. Well, I guess it's supposed to be safe, and it has a lot of Rust running on it. So I thought the name was appropriate. And also, I mentioned the name to people that have no idea of any Rust or whatever, and they think it's a cute name. So I guess it kind of works out. Here's another picture, just so you can see what it's actually like sailing, just in the harbor. So here's just some basic statistics. It's a racer cruiser, which basically for me, the definition is that it has an enclosed toilet, so you don't have to do your business in a bucket in the middle of the cabin. It's about the size of an RV, like a medium-sized RV, weighs a little bit less, but it has a 45-foot mast, so it's a lot taller. So most importantly, I guess at the bottom, it comes with a suite of components, sailing instruments and computers from B&G, who is one of the major manufacturers of sailing electronics equipment worldwide. So those components, they're actually pretty good for sort of traditional sailboat racing. I guess they'd be considered a medium level suite. And when you're racing with 4 people or 8 people on a boat, for short races, they actually work fine. You can afford to have, it's like operating a GPS in your car, or you can afford to have somebody go down and spend time looking at it and fiddling around with it and playing with the touchscreen to do stuff. But I'm interested in actually a very different kind of racing, solo offshore distance racing. So it has a really different set of requirements. And so I wanted to start with those particular instruments and then build something that's much more adapted to those requirements. So first is safety. So offshore sailing is inherently a risky sport. It's not extremely risky, but it's something where there's a lot of things that can go wrong. And when you start racing and you're doing it solo, then you start adding additional risk on top of that. And so I wanted something where figure out how can I use these systems to sort of claw back some of that additional risks to manage that, so that it's just safer and there's less things that are going to go wrong. I think I wanted something that's easier to use. So, I mean, just physically, it's a tough environment to work in. There's bright sun, there's nighttime, there's rain, you're going to be wearing gloves, your hands can be cold. You may even be at different places on the boat where you don't have access to the controls. So I wanted to figure out how can I improve on that. But then there's also sort of the mental aspect of making it easier to use. When you're solo racing, especially in multi-day races, a lot of times you're going to be operating for extended periods at basically 10% of your mental capacity. You're going to have been up for 24 hours, 48 hours. Typically, multi-day races, sailors will actually go and then be awake for 2 hours, sleep for 10 minutes, be awake for 2 hours, sleep for 10 minutes for like days at a time. So you have to make it so that things just work and that you don't have to use a lot of your cognitive ability to get things to do what they need to do. I guess there's a lot of technology that's already on the boat, which is integrated, but in a very superficial way. So in a lot of cases, you have things that are going to be displayed on the same monitor. But as far as actually having systems use that information in any kind of useful way, it just doesn't happen. They just haven't done that kind of integration. There's also, and I'll get into some specific examples, there's cases where there's other tools that you may be using that are not going to be running on those systems, that are going to be running on something like a laptop, that are going to be completely disconnected from the built-in systems, and you have to manually figure out how to connect those things together. So I wanted to have something where you don't have that, because the next piece of that is having better automation. So right now, the sailboat has a built-in autopilot, which is pretty much limited to going saying, okay, go that direction, hold that direction. Maybe say, okay, hold that direction, but adjust it if the wind changes. Especially for solo offshore sailing, you really want to get as much help as you can, because there's just a lot of other stuff that you can't automate on the boat. So if you can get the boat to go and then do a higher level of using all this information and doing more things, that, being able to take over more things, especially when it could do it better than you because you're at 10% capacity, then you're going to be doing a lot better. And then finally, better performance. So some of this is simply, okay, can I write an autopilot or improve the autopilot so that it sails maybe half a knot faster, or a little bit faster in certain conditions. That's definitely something you want as far as racing goes, sort of at the tactical level. But what's even more important is that I'm able to make strategic decisions, like which route am I going to take? When am I going to attack? What sails am I going to put up? How can I get around this weather system? So those are the types of decisions where if you can make those decisions better, like that's basically, if everybody else doesn't make the turn and you make the turn, you can win the race by 12 hours, like a whole day. So getting to the point where you can go and the system can help you make those higher level decisions that have a huge impact on like who actually wins and loses the race, much more than can you go half a knot faster in a particular wind condition. So I guess 2 specific examples. So the first one I've sort of been hinting at, continuous integrated weather routing. So weather routing is where you go and you use weather forecasts, specifically different types of wind forecasts. You use the model of how fast your boat will sail in different conditions in different directions, and you basically do an A-star search from where you are to where you want to go to figure out what's the best combination of sailing directions to get to where you want to go. So right now, there's some excellent software that people use to do this, but it's generally running on a Windows laptop that you have to go and operate below decks. And on big boats, the way they do it is they have a crew member, that's his job. He goes down every 2 hours, maybe 3 hours. He goes down to the nav table with the laptop. He goes and hits the button on the satellite to go and download whatever map files, the latest weather forecast. He'll go and then tweak whatever it is, and he'll go back up to the helmsman and say, okay, go and just sail 327 for the next 30 minutes. And that's his job, which is great if you have 8 people on the boat and you can afford to do that. Plus, that's probably the person on the boat that gets the most seasick, because he's down there staring at the computer while the boat's kind of going all over. So a lot of cases, shorthanded sailors race in these races, they just can't afford to do that. They can't afford to go down below and spend the time to go and do that properly, or they just may not be willing to. So in a lot of cases, they just go and they will do the route planning up until the start. And then once they're at the start, they're locked into that particular route. And they'll follow that route no matter, maybe if they're lucky halfway through, they'll take a look at the weather and adjust it. Which isn't ideal, but what are you going to do? And so you can think of the existing process as an offline batch process. It's an offline manual batch process. And what I want to do is to figure out, can you turn that into an online continuous process where the system will automatically download the latest weather files, update the route, run the routes and update the predictions, and then either just go and tell the navigation system, okay, let's go start sailing this particular route with enough feedback so whoever's sailing can go and actually look and see, like, well, does that make sense, or is that gonna just not work? I guess another one, and I'm calling this automated least cost avoidance maneuvers. And so what this is when you're sailing offshore, you have to deal with other vessels, commercial traffic, fishermen. So there's the technology called AIS, which is a type of special radio beacon that all ships over a certain size are supposed to broadcast. And it basically provides their GPS location, their heading, and their velocity. And it's line of sight, so you can get about 25 miles of range, which is great because now you get about, call it about like 2 hours before this tanker is going to run you over. You know what's going to happen. So this actually is an incredibly valuable tool, and most vessels, especially over a certain size, now have tools. And this, my boat also has some basic tools to go and then do calculations, simple calculations for, what's the closest point of approach between these two vessels. This is called a CPA, which says what's the closest point, and TCPA, which is how long is that, when is that going to happen? So that's incredibly valuable. That's actually built off of pre-existing tools that were done for radar. But then you think about it, it's like, well, calculate that based on a straight line, and then you can set an alarm, but it's a pretty primitive alarm. It says, generally you can say like, well, if it gets less than 800 meters, if it's predicted to be less than 800 meters, or if it's predicted to happen in less than an hour, then raise a really obnoxious alarm. So even if you're sleeping, it wakes you up and says, there's a vessel, you got to take a look at it. So immediately you think like, well, what's the right way to set that alarm? Because that's a tricky trade-off. You definitely don't want to miss these cases, but you also don't want a lot of false positives, because those things, like if you're trying to sleep and you're getting false alarms that you have to go up and deal with, that's actually cutting into your own performance. And not to mention the fact that at some point, if you keep getting these alarms, you're going to try to turn them off or set them so that they're not constantly bothering you. The other thing is that once that alarm goes off, it doesn't tell you anything about what you should actually do. So it doesn't. So you still have to look at the situation and decide like, well, do I just keep going straight and it's going to be okay, or do I turn right? Do I turn left? What happens if they speed up or slow down? You have to figure that out all by yourself. And there's tons of mistakes you can make. You can turn right, and it turns out that it brings you closer to a collision. You can turn, and then it turns out you're going to collide. You're going and go crash into another vessel. Or you could just not notice that you're turning, and then like, oh, well, there's a small island there that I forgot to look at, and that's a very bad situation. So one of my goals, and this is sort of a medium to longer term goal, is to make it so that this system can take a lot of different information from the AIS, from the charts, even the weather information, and help come up with what's the best maneuver to do, especially since if you're 25 miles away, you can make a very small maneuver and be able to go and then avoid a ship. Whereas if you wait until you're a mile away, you might have to make a pretty radical maneuver to avoid the ship, and that might be slow if you're racing. So it's sort of getting into the hardware architecture. I'll try to go through this pretty quick. Let's see. Oh, it's jumping back and forth. Well, the bottom layer is CAN bus. So boats use CAN bus. There's a protocol called NMEA 2000, and that's one of those sort of open but not really. You have to be a member of the association, which costs about $8,000 a year in order to get access to the official documentation for the protocol. And there's NDA, so that if you have it, you can't just go and publish it in your open source code. And they actually have a clause saying you cannot republish this information in an open source library. So fortunately, there are a lot of people that have actually gone and reverse engineered or used different techniques to go and figure out a lot of the messages. So that's helped. So you can see at the very bottom level, there's a lot of sensors that talk there. Now this here, I guess I'm going to call sort of like my soft real-time system. It's currently built around the Raspberry Pi. It talks of most of the components via USB. There's a USB to CAN bus adapter that actually talks to NMEA 2000. I have some additional hardware. So RTK GPS that's a particular technique of using GPS where you can get the relative position of two receivers to within about a centimeter. And so that I use have two antennas on different sides of the boat, and that can give me the absolute orientation of the boat very accurately, and also to some amount the roll. I also have one receiver on the end of the boom, which is the piece that swings back and forth holding the sail, and that provides some very valuable information that I'm going to figure out good ways of using. There's a 9-axis IMU, which basically gives very good information about the physical movement of the boat. So I actually have that connected via a Raspberry Pi Pico that goes and connects it to USB. There's a SDR. I don't know how familiar everybody is with software-defined radio. The original reason why I wanted it is, and I still want to implement this, is so that I can do scanning of all the VHF marine radio frequencies and record all of the audio transmissions that are getting transmitted by people, so that there's never a chance of missing something, so that if you hear a radio message, you didn't catch it, you can always go back and listen to it again, which can be pretty important in some cases. But right now I'm actually using it for ADS-B, which is kind of like AIS, but it's basically what airplanes transmit their locations over the air to avoid collisions. And that's actually kind of for fun. There's not a practical application of it yet, but it actually makes for a great demo. And I just like seeing that information, like what planes are flying overhead. And then finally, I have a loop deck connected, and I don't know if anybody's used a Stream Deck, any of those. It's basically a tiny little display with a bunch of programmable buttons. And that's just a nice user interface to the Pi, so I don't have to have a keyboard and display connected to go and do things. And then finally, I do have a simple metrics display, which is basically a simple 6-inch display that just shows a lot of basic telemetry, like how fast I'm going, the wind direction, a couple other things like that. And then I guess on top of that, then I actually have, right now I'm using my laptop, but probably will be converted to a Mac Mini at some point for doing some of the stuff that the Raspberry Pi can't do. So that gets into the chart display, and then the voice input and the voice recognition and the voice output, which can't quite run on a Raspberry Pi class system yet. And that's connected over Ethernet. And then the software architecture looks pretty similar. There's a lot of drivers which are basically just Rust processes that talk. A lot of times, in most of these cases, just talking over a USB serial port to whatever virtual device it is, and then basically puts that into UDP multicast packets, so that I have a bus where anybody that wants to, any process can go and write and read from that. So you have a couple of different protocols that it's talking to. I also have some firmware, Rust firmware, actually running on the Raspberry Pi Pico, which actually does the translation from the IMU over to USB. Let's see. At this next level, I'm calling the compute level, which is where a lot of more interesting stuff is doing. Probably the most important thing here is a Kalman filter. So that's doing the fusion of all the different sensors and predicting how the boat's maneuvering. It's also doing a lot of boat physics calculations, so estimating what direction is the wind coming from, calculating what's the current, and even keeping track of things like, what's the rudder doing, what are basically all the boat state it gets consolidated in the Kalman filter. And there's a couple other things here. I won't go into too much detail, except the utilities covers actually a lot of really important stuff, which is almost worth its own talk as sort of a practical, like I record, pretty much typically record every packet that goes off, a timestamp packet that gets transmitted onto that multicast bus, and just log it. And then I have some utilities that can go and play that back in whatever real time, which is just incredibly useful for being able to go and say, here's something that happened at a particular time. I want to just play it again, update my software. Maybe there was something that didn't work right. I want to see exactly what it looks like. So you can basically record and play back anything that happened on that boat, and all the state should be in there. And then there's also kind of almost like a Wireshark type thing where you can introspect all those messages. So both at the raw binary level, but then some of these messages have some additional context, or you want to interpret them as autopilot messages. So what does this autopilot message mean? So being able to go and introspect all those messages is really valuable for understanding what's going on the boat. And then we have applications for the metrics, the chart, the voice input output. I just wanted to put in the corner, there's two big major data sources that I'm using. One is this format called S57, which is what NOAA and other organizations use to publish electronic navigational charts. And that's the standard. Basically, that's the standard everybody uses. And then GRIB2 is the format that basically every supercomputing weather forecasting center uses to publish all of their data. And some of these are just absolutely huge, like EMCWF. They'll produce a model that has like 5,000 parameters every 6 hours. And that if you downloaded the entire thing at once, it would be like a terabyte of data. And so you don't have to get all of it at once, but that's the format that is kind of universally used to go and then retrieve it. So, so some of this stuff, I guess people want to ask me about it because I'm sure I'll run out of time. Basically, there's really only about 4 processes. The CLI is just this big multi-layer level nested CLI. SDL2 is basically the instrument display, and it's using the SDL2C library because that's the only tool that I have right now that will let me do window manager less accelerated display on the Raspberry Pi. N2K Vello is something I'm going to show next, which is using Raph Levien's Vello. I don't know if you want to call it a 2D GPU accelerated rendering library, which has been like just amazing. It's built on top of WGPU, so should be cross-platform. And I have gotten toy applications running on iOS, so hopefully I will get there. And then the speech recognition stuff, which wraps up a couple of different interesting packages. So let's see. Yeah, so let me see if I can actually go and get this actually working. So this is the challenge. So I'm going to actually go and run. Okay, so let's see what this looks like here. Yeah, we'll do this full screen here. So I don't know how well this will show up on the screen share, because just because the screen share Google Chat is probably only going to do it at like whatever number of hertz. But you can see here, this is a playback of, I don't know, Ben, this actually could be our sail when we went out, because I'd like this is June 2nd or something like that. And so this is actually pretty fun because you can see here, that's where the boat is. We have some stuff to indicate, how fast the boat's going, the direction it's going. The green line indicates what direction the wind is coming from and how strong the wind is. And you can see it's tracing it out, so you can see the history of that. There's some instrumentation here, so you can see some information about how fast the boat's going, which so on. But you can also see, this is the yellow stuff is all the AIS data. So you can see all the different vessels as they're coming in and out. So it's actually a pretty busy day. You can see, the Independence is going out. There's all these different boats passing us. Yeah, and then you can see the JetBlue flight kind of came by. You could just look up that tail number, and you're literally. I kind of do want to add something so you can just. So like when a plane's about to fly over, it just says, hey, JetBlue 217 is coming over. And so in fact, I'm going to zoom out a bit. And so one of the things is you can sort of, as you can see, and I'm going to hide some of this stuff, the scale. I mean, it's pretty amazing. You can just pick up what you can pick up. And this is actually what, if I had this running on the boat, this is actually what I would be seeing. So you can actually see the planes coming out from like on their approaches. This is the extent of this particular map, and you can see how far out. Like these are actually beacons that are on AIS, and eventually you should see all of the different vessel identifiers. And I know it's hard to tell from that, but if you scroll in and out, it's like absolutely smooth. It will just scroll in and out like at 60 frames per second. And you can slide it around. You can rotate it, and you can see there's a bug where, this is aligned with the boat, but the text really should be aligned with the screen rather than aligned with north. The nice thing about Vello is that it has basically kind of like all the primitives that you would use in Skia, Tiny Skia, or SVG. But you can kind of basically, you can sort of create fragments and then throw them over to the GPU, and then the GPU in parallel renders like the entire thing. You don't even, there seems like there's no performance penalty for how much stuff you throw over in most cases. And so, in the previous version of this, I was displaying the maps, but you have to put in your work to go and then clip and then simplify stuff so that you're not over, so you can keep your frame rate up. But this one here, when I load up the program, I load the chart, and I just basically render, I do all the path commands for the entire map once, and then basically that's it. And from that point on, I'm just updating the transforms to say, okay, should I zoom in and out, rotate, anything else? I guess really quickly, another thing, actually, I didn't actually have it on here. So I also have the ability to go show the weather. Let me see if I actually have that. So this is a similar thing here, but it can actually overlay weather forecast with the representation of the wind. You probably can't really see the animation, but this basically is a pretty easy way to see which way the wind's coming from. And I guess this is the one exception, is like if you go and you load a grid file that has like 100,000 by 100,000 elements in it, and then you try to build that many little wind arrows, then you will run out of resources on your GPU, at least my GPU. But Vello doesn't care. It's just going to run. It's just going to be like, oh, I ran out of texture memory or something. So this has really been a lot of fun to have running. So that's Vello. And let me actually stop. So this is the part where I see if things actually work.
Ready.
And I don't know if you can hear this here. So what I'm doing is actually starting up sort of a simulated boat. Oops, not play demo. I want. So what's going on here is that I actually have, I'm using Whisper. Let me see if I can find which. Yeah, so pilot status. So pilot set undocked. And so you can see the status. Pilot prop up. Pilot prop up. Pilot motor idle. Yeah. So this is the reason why you don't do voice recognition demos live. But let's just try it one more time. Pilot status. Yeah. So sometimes what can happen is it can hear itself. Usually I do this with headphones on, but then you can't actually hear the output. And in fact, I don't even know which microphone it's using. That might be part of the problem. So basically what this is, let me see if I can get to a slide that will just show you really quickly. So I'm going to turn this off. In fact, maybe it was using the wrong microphone. So maybe I'll give anybody that wants to try it out afterwards, that might be a better time when nobody's paying attention to it. Okay, so there's a couple components that we're using. I don't know if anybody's familiar with Whisper.ai. So that is the speech transcription tool that OpenAI has kind of thrown over the wall. So somebody's actually written a very nice C++ wrapper that's basically a player that can load that model and run it on a lot of different hardware. For instance, on this Mac, it will actually use Core ML to actually display the, actually run all the neural networks. So it's designed for transcription, which it does an extremely good job at doing long form transcription. But my use case is for doing intent recognition, where you actually have a much more limited grammar. So I've done some work where basically you go and I can get into, anybody who wants to talk about this, I can go into some more detail. But basically what you do is you actually build, it's almost like building a language grammar of all the possible terms, all the possible words that you're expecting somebody to speak. And you're going to have a big tree, including things like somebody's going to have a number, and it's going to be between 0 and 360. There's only a certain number of phrases that are going to be valid. And you do partial matching along the way in order to constrain the speech recognition to only give you things that look like they would fit your grammar, or else reject it if it just doesn't make any sense. There's another tool called Celero, which does voice activity detection. So it'll automatically know when you're speaking and when you're not speaking. There's another tool called Piper, which actually does the actual voice synthesis. And again, that is a C++ project, but the actual models are kind of language neutral. And so right now I've been running these on Apple Silicon, like on my MacBook Air M1. And like I said, the Raspberry Pi can't quite handle it. It can handle the simplest models, but I wanted something with a little bit better performance. So hold on, let me see, get it to stop trying to recognize what I'm saying. You could see a pilot status. Pilot, turn starboard to 360. Now, pilot starboard to 350. I gotta turn it off for now. Okay, let me just get to the conclusions. So let's see, did that come up? So first, it's just awesome having a language that can just cover this dynamic range. So I say from SPI to CLI to UI to AI. It's just amazingly valuable to be able to go and just jump between different components, especially if you're working on a UI component and you realize that you really wish something at the lowest level was sending some data in a different way. You can just go and open 2 files and fix it, or even have a single library that maybe you add a new field to and be able to just fix the problem. You don't have to go and do that context switching, just go between Python and C and whatever. I think a lot of this stuff is running on the Raspberry Pi. And so you absolutely have to deal with getting your cross compilation set up if you're going to do anything serious. And it's all doable. I think it could be, there's a lot of work to make it more user-friendly, because it took me a lot of pain to figure out how to get some of these things set up, especially since the Raspberry Pi is kind of in the middle of a 32-bit to 64-bit transition, and that sort of makes things harder. And plus Docker, and at the same time, Docker is going between, on the Mac is going between the x86 and the M1, M2. So there's a lot of moving parts. You can make it work, and it's worth putting the effort because it would take like about an hour to compile the binary on the Raspberry Pi. I think language safety lets you focus on domain safety. So every minute that I don't have to worry about dealing with ownership problems. I mean, this stuff running just never crashes. Sometimes the devices will disconnect from the USB bus and something will die. But things don't crash. Now I run into other issues where I'll get floating point issues, I'll get infinities or nans, and I have to figure out why those things are happening. And so you get to focus more on sort of the domain safety issues, which are really big deal when you're sailing offshore. I think I said before, monolithic CLIs, it's great to be able just like, instead of writing a script, just add an entry to your clap configuration, add a function someplace, and all of a sudden you have something that's built in and you can extend that forever as a single tool. I think Vello is just amazing. And I think there's going to be a whole generation of UI toolkits that use Vello as their base. And especially as Vello goes and starts running on more and more platforms because of its using WGPU, I think it has a great, it's such a great graphics model and concept. But you don't even need to use a toolkit. You can just write Vello straight and get some great results pretty easily. And then finally, I think there's actually a case to be made that Rust can actually replace Python for a lot of actual real world AI applications. So I'm not talking about training, but about inferencing. So when you have a voice recognition tool or like a ChatGPT equivalent or something else, I think in the short term, a lot of those tools are just incredibly hard to get running if you just start from scratch and working in C++ or whatever. And everybody knows what it's like to try to get all your dependencies working and fighting with CMake. So just the fact that you can include that somebody can package up these libraries, make it so you can just add one line to your cargo and then start playing with it and have a great high-level API and documentation is just amazing. And then in the long run, a lot of these, there's a couple of different Rust, I guess you call inference players that will actually do the actual heavy lifting of running these models. And they're not there yet, but I think in the next couple of years, it will get to be the point where we will have Rust native tools for running these neural network applications and then be able to just pull them together. And so hopefully it made sense.
Two questions. So pick.
Okay. There you go. Oh yes, sonar would be great. You know, it's tough to tell exactly. There's some of these projects, I don't know, sometimes it's like you have a vacation and you're just bored, so you decide to write a grid parser. That's just how it goes. I don't know about sonars, but actually one of the applications I have been thinking about is there are a couple over-the-air protocols that the FCC is standardizing on for tracking drones and surface vehicles. So you can imagine using an application like this, but to track a fleet of drones. And that's actually one of the reasons why I added some of the ADSB stuff, just to see like, oh, I wonder if you could use it for that. Do you have a question? Yeah.
I'm sort of wondering, this might be a stupid question, but like, have you compared this or talked with anybody in, say, the Coast Guard about what their setup looks like? How, just for inspiration or?
Yeah, no, you know, I have actually talked with, there was a friend of mine at MITRE who did say that the US Coast Guard was doing some amount of port modernization. So it's some, you know, they do have some projects go on, like, so for monitoring what's going on. So I think at some point I am hoping to talk to them to get an idea of what they're interested in. And I think there's also a lot of work going on in the industry for let's see, unmanned, unpersoned surface vessels. There's actually a startup out of Boston that is doing that, and there's at least a couple of them in the area. So I'm starting to get to the point where I feel like, okay, this is enough to go and approach somebody with to say like, hey, how does this compare to what you're doing? Is this something that might be useful?
You have one more question? Yeah, here. Okay.
I was just wondering about your experience developing for the Pico.
Oh, the Pico. I have not done a ton of development for the Pico. I just used the I think I just used our Pico HAL crate. I felt like definitely for the simple stuff, it actually worked great. I mean, like the SPY and the I2C worked well. And then once, I mean, the USB stuff, it's always something where it's a little bit of adventure to get it running, but once you actually get it running, you don't have to mess around with it very much. And that's been absolutely reliable. So I've had good experiences. I do some point want to experiment a bit with the PIO stuff, because there's a ton of really neat stuff you can do with that.
So, well, we are being talked to Twitch right now.
Oh,
So
okay.
we'll
Do
take
they
one
have
of
a
the Twitch
question?
Chat questions.
Sure.
Pick
What is
one of those two that we have right here.
Let's see.
Can you repeat it out loud too for everyone?
Okay, so how do you use Rust to model and handle wireless device disconnects and reconnection attempts? So I think right now I'm not using too much wireless on the boat. Most of the things I've tried to use, like Bluetooth, have been too hard to get working reliably. I actually found out the hard way the other day that if you boot up the Pi, which does not have a built-in real-time clock, and then try to log into any kind of wireless network that it's running, it will not let you log in because the clocks are going to be out of sync, and it's going to say that it's invalid. So I haven't done a lot of, I think that's actually kind of something I've been trying to avoid, is the whole like wireless reconnect and disconnect. In fact, most of the times the stuff that I'm doing, if that happens, the right thing to do is like you panic, you exit, you let the supervisor boot you up again and retry every like 10 seconds until maybe your device eventually comes back online. And sometimes that's the easiest thing to do, is not worry about it too much.
So thanks again.
Thank you.
Anybody have any questions? We'll be here for half an hour or so feel free to finish off this pizza. Mingle. If you have to leave, then go ahead. But